Um, this is the second part of the video on logs, section 3.2, and we're talking about the properties of the log, and I like to think of it as the inverse, where the actual main function is f of x equal a to the x. And we're going to look about applying the inverse properties and also some important formulas. And then I want to also let you know that we are not covering transformations of the log. So those graphical transformations of the log, you can skip, and it won't be on an exam. Okay, I want to do a quick review, and I think the review will be helpful if we have a certain, just have an example in mind. And we saw in the last video that 1.963 was about equal to 92. And I just want to keep that in mind. Okay, so we have a function, f of x equals a to the x. This is an example where a is equal to 10. So f of x equals 10 to the x. And using this, f of 1.963 equals 10 to that number, and then that's equal to 92. Okay, so what happens to this function is you plug in an exponent, and you get back a power of 10. So we have the inverse, and that's going to be the log base a of x. So in our example, f inverse of x is going to be the log base 10 of x, and that's often abbreviated just as the log of x. So if you just see the log of x, you put a 10 there. Okay, so that would mean that f inverse of, remember this inverse is this relationship, so we plug in our number, that's a power of 10, and that's going to be equal 1.963, and we get back the exponent. So we plug in a power of 10, get back an exponent, and the main function, it's the opposite. That's what an inverse does. And we have a special notation for the inverse of 10 to the x. As I mentioned, it's the log base a of x. Okay. And here's what I think. One way that I keep track of things is if I think of the log x equaling some number, let's call it c, what that means to me is that a to the c is equal to x. So a to the c equals x. And I also think it's important to keep in mind that logs are exponents. So when we plug in a number into the log function, we get an exponent. Again, let's look at this, log base 10 of 92. That says what exponent of 10 gives me 92? The answer is 1.963. That's an exponent. That's the exponent of 10 that yields 92. Okay. Again, I wanted just to kind of review that stuff. Another thing I want to review some notation. The log base 10 of x, as I mentioned earlier, is just basically the log 10 of x, and that's called the common logarithm. Then we have another special base, log base e of x. That's ln of x, and that's called the natural logarithm. I did not make up these names. If it were up to me, I would leave the numbers in and not give them special names, but that's me. Okay, so I wanted to remind you this. So what I'm going to do is look at the graph of y equal e to the x, and then y equal natural log of x. And then we'll also look at we'll also look at this one, just for variety. Oops. Y equal log base 10 of x just equals the log of x. Okay, so I'm going to share and jump over to Desmos. Okay, so here we have e to the x in blue up, or purplish up here. We have the line y equal x, and then we have the natural log of x below it. And the x, the inverse switches x and y, so notice that we find the point 0, 1 on y equal e to the x. We're going to find the point 1, 0 over here. Now here, we see a point, it's hard to get exactly 5, but do the best I can. I get 1.615, and then when I go 5 here, you're going to see it's reversed. Sorry, right here. It's hard. I can't. There you go. You can see it's just reversed. Okay, it's 5 and 1.61. So again, when we switch x and y, we reflect across the line y equal x. Okay. Now here, let's just look at 10 to the x and the natural log of 10 to the x. Okay, and you see it's the same relationship. The graphs look pretty much the same as, I'll switch them back, as when I had e to the x and its inverse the log of x. We're going to have that relationship. So no matter what I put in here, if I put, instead of e, if we put 13, and we had the log of 13, which would be kind of crazy, again, you're going to see that they have that same look to one another. Okay. So I wanted to go over that. I also wanted to make a little table about the inverse, just to make some comparisons, and then we'll go to some applications. Okay. So here we have, let's use y equal 10 to the x. And then we saw that the graph down here was y equal natural log of x. And so what I want to do is I want to make a sort of comparison table of f of x and its inverse. And I'll emphasize that we're doing 10 of x. The reason I'm doing this is to reinforce things that we talked about earlier. So here's the domain. We saw that the domain of 10 to the x was minus infinity to infinity. And that's because you can plug 10 to any power is okay. That's allowed. Okay. The range is 0, infinity. Again, you can see the graph is always above. And why is that? That means that 10 to any power has to be positive. Think of multiplying, 10 by itself a few times. So what happens with the range is it flips. The range of the remember this earlier, the range of the function is the domain of the inverse. So that means that powers of 10 are always greater than 0. And over here, remember we get back the exponent. So this tells us that all exponents are allowed. Okay, a couple of other things. Y-intercept, let's look at the two of them. The y-intercept of 10 to the x, we plug in x equals 0, we get 10 to the 0, that's 1. There's no y-intercept because 10 to the x equals 0 has no solution. Okay. Now we look at the x-intercepts. Guess what? We have the log base 10 of 10 is equaling to, the log base 10 of 1 is equal to 0. And that's because 10 to the 0 is equal to 1. That's how we get this point right here. And there's no x-intercept. So you can see these switch. Okay, I'm going to do this one more time. And asymptotes, we have horizontal asymptote. We see that here, y is equal to 0. The graph approaches here. So as x goes to minus infinity, the graph of this function approaches 0 from above So we get y equals 0 is the horizontal asymptote. Looking here, there's none. And then vertical asymptote, we see there's one at x equals 0. In other words, as x approaches 0 from this direction, so from the positive side, y goes to negative infinity. Just the reverse of this. And there's no, the exponential function has no vertical asymptote. So again, I just want to emphasize the way that things switch. And again, this is the way we see it. Something like this, 10 to the 1.963 is 92. The log base 10 of 92 is 1.963. Okay. Okay, so I want to do some applications, and that will be it. I'm going to do a theoretical application first, and then we'll do some problem solving. I just had a few solutions over here that I wanted to go over. Okay. We'll do a couple of problems. So we know that for any inverse, this is true. That's true. I'm sorry. X is equal to f times the inverse. They undo each other. And likewise, if I start with the inverse, I have that. So if f and f inverse are functions, then this always is true. Okay. So I want to look at this. This gives us a weird identity. So I'm going to look at this for f of x equals 10 to the x, f inverse of x equals log base 10 of x. So x is f inverse, so f is 10 to the x, so that means that this is going to be 10 to the inverse. That means the inverse is 10 to the log base 10 of x. And notice we get x. That's what we started with. We still have x over here. So I think of that as cancellation. Okay. Likewise, if we start with the inverse first, we get f inverse is a log base 10 of f of x. That's going to be the log base 10 of 10 to the x. And what does that equal? Well, we started with x. This is all equal to x. So that's x. So that cancels. Okay. So basically, we have this identity. And you'll see this in other classes, that a to the log a of x is equal to x. A's cancel. Likewise, likewise log a of a to the x is also equal to x. So these are important things to keep in mind. Okay. So just some applications of the inverse. We talked about this before. You might have something like this, e to the natural log of 7. And they might say simplify. Well, remember this is e to the log base e of x. That's what the natural, of 7, I'm sorry. Those cancel, we get 7. So again, a was equal to e, we just apply that. 2 to the base 2 log of 13, same thing. That's, again, going to be a version of this. That's going to be 13. And likewise, we have the natural log of e to the 52. That's going to be the same as log base e to the 52. That's this identity here, so that's going to be 52. That stuff cancels. Likewise, if we had the log of 10 to the 6.2, remember when you don't write the log, when you don't write the subscript, it's assumed to be base 10. And that's going to be 6.2. Those cancel. Okay, so I just wanted to go over that. And I want to go over one more example, and then that'll be it for this video. So this was the other application. Let's say we want to solve 10 to the x is equal to 32. Now you solve that. I'm going to give you a minute. I have to go look up the video. Go look up the exponent. So I'm going to go do that. So I'm going to go, okay, what's the log of Okay, good. So forget that I did that. Oh, I didn't show, so let's go back to the main screen. I said, okay, well, this relationship tells me that the log base 10 of 32 is x. And I went and looked that up, and that was about 1.505. Oops. Sorry, that was gawky. I dropped off my pen. Okay, so that's another one. Is when you see this relationship, transform it to the log relationship. And finally, you'll get some problems in WebAssign like this. They will say write something like this. Write 2 to the 5 equal 32 using logs. And the way to do that is log base 2, 32 is equal to 5. Remember, that's the exponent. That's the base. The log is finding the power of 2 that gives us 32. And they might say something like this, write a log relationship, like we have the log 10 of 1,000 equals 3. They'll say write that in exponential form. So what they want you to do is just to rewrite it using exponentials. I'll do that circular thing. 10 to the exponent is equal to what you're taking the log of. Okay, so you'll see some examples like that. Okay, well, that's it. Thank you.